problem 15 here. We have two boxes, 5 kilogram one, which I'll call little m, and 8 kilogram one, which I'll call big M. The coefficient of kinetic friction between each box and the floor is 0.5. So we want to know first how hard I have to push the 5 kilogram box so that the pair slide together at constant speed. Doesn't matter what that constant speed is, but the fact that it's constant speed is important. If I look at both boxes as one system, then the force they exert on each other would be internal, and we wouldn't have to worry about it. We only need to worry about forces exerted on that whole system from the outside. So I could think of this as sort of one big box. There's a normal force, and there's a weight, and the weight would be the combined masses times g. I'm thinking of these two boxes as just one big box. So if I'm pushing the 5 kilogram one, they're sliding to the right. There'll be kinetic friction to the left, and I'm exerting a normal force to the right. I'll call up and right positive arbitrarily. So F net for both in the y is n minus m plus mg, and it's 0 because it's not accelerating in that dimension, and they're also not accelerating in the other dimension. So normal force exerted by me minus friction, balance forces as well. Notice that this normal force here is the normal force between the surfaces, so that's the first n. That's not the normal force that I'm exerting. So this is the normal force I'm exerting, and the friction force cares about the other one, the one that's perpendicular to it. So I'm trying to find normal force that I exert. So normal force of me is mu sub k times n, and as you can see, n is m plus mg. We know all those numbers, so we can say that's 0.5, that's 13 kilograms total, and that's 10 newtons per kilogram, so this will be altogether 65 newtons. Now if I push the thing to the left instead, the friction force is on the other side, the normal force is on the other side, but nothing else really changes. That's the answer for A and B. So all I'm doing is flipping which side I'm on, if I only look at the whole system. If I want to look at the forces the boxes exert on the force the boxes exert on each other, then I need to consider them separately, and things do look different. So let's do that. Let's look at these two separately. So let's look at little m. So let's say I'm pushing to the right. So normal force me. A little more room here. Okay, normal force me, which we know how big it is actually now. It's mu sub k times m plus mg. Backwards, we have a friction force, mu sub k times normal force on the little box. Okay, and the normal force on the little box is based on its weight, right? Because this is just for little m. Also, the big box pushes back against it. I'll call this n box. This is the normal force between the boxes. Imagine yourself in the place of this little box as you're being pushed forward. Friction's pulling you backwards, but also you're being squished against this box, so that box is pushing you backwards as well. If I look at the big box, I have a different n, so this will be n2, this will be big mg. The force pushing it forward now is only this n box, because I'm not touching this one. And Newton's third law applies here, right? These are the normal forces between the boxes, so those are equal but opposite directions. And then the friction is backwards, mu sub k n 2. So I'm not exerting a force on that 8 kilogram box at all. Okay, if I look at the F net equations, F net little m in the y, n1 minus mg is 0. F net big M in the y is the same, except big mg. In the x is where it's interesting. F net big M in the x is n box minus mu sub k n2, and that's 0. F net little the normal force that I exert minus mu sub k n1 minus n between the boxes, also 0. Okay, so in this case, we're looking for n box. We're looking for the force exerted between the boxes. And that's actually pretty easy to get if we go from this equation. N box is mu sub k n2, and n2 is really easy to get from there. That's just big mg. Alright, so that's the force exerted between the boxes. Whatever is the force between the boxes is pushing the big one forward, which has to counteract the friction and balance it exactly, and we know how big the friction force is on that box. That's pretty easy to find. So in this case it would be 0.5 times 8 kilograms times 10 newtons per kilogram, which is just 40 newtons. So let's check and make sure that everything checks out just to be sure. So n me was 65 newtons, n box is 40 newtons, so hopefully mu sub k n1 would be 25 newtons, and mu sub k n1 would be mu sub k little mg, which is 0.5 times 5 kilograms times 10 newtons per kilogram, which is 25 newtons. Okay, so everything checks out. It's all, we went through a lot of stuff there, so I want to check that just to make sure I didn't make a mistake. If that all didn't add up so that the net force on this one was 0, I'd know I need to go back and fix something. But it all worked out okay. So this is pushing the 5 kilogram box. What if I'm pushing the 8 kilogram box? Well, all of this is basically the same, except I'm swapping little m and big M. So I could just do that in all of my equations as well. Just swap big M and little m, and that will give me my new stuff. So if I use that symmetry, this would end up being little mg, because little m would be the one that's in front. So 5 kilograms, 10 newtons per kilogram, and that'll be 25 newtons. So if I'm pushing the 8 kilogram box. So the force between the boxes actually depends on which one you push. So if you had like an egg and a box that you were trying to push, you would want to push the box. Right? So this is where I'm pushing the bigger one. The force between the two objects is smaller, because if I push the egg, the force between the two will be big and then squish the egg. If I push the big one instead, the force between the two will be small and the egg will be safe.